Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm so glad you're here with me tonight. We're about to embark on a journey that will take us home, not to the place where you were born, not to the house where you grew up, but to our cosmic home, the vast spiral of stars, gas, and mystery that we call the Milky Way galaxy. Tonight we'll drift through facts so extraordinary they'll reshape how you think about your place in the universe. We'll explore the hidden secrets of our galactic neighborhood, uncover mysteries that have puzzled astronomers for centuries, and discover truths about our cosmic home that are more beautiful and strange than any science fiction story ever written. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination soar through the spiral arms of our galaxy. There's absolutely no problem if you doze off midway through this cosmic journey. Let your thoughts drift like stardust through the galactic plane. If you find comfort in these gentle explorations of our universe, I'd be grateful if you'd consider subscribing and liking this video. And I'd love to know where you're listening from tonight. Are you under the same Milky Way that has watched over humanity for thousands of generations? Feel free to comment your time and location below. Let's start. You step outside on a clear, dark night far from the city lights. Above you stretches a faint band of light across the sky, like someone spilled milk across the heavens. The ancient Greeks saw this celestial river and called it Galaxius, meaning milky. The Romans called it Via Acta, the Milky Road. But what you're seeing isn't just a beautiful sight. You're looking at your cosmic address from the inside. We live inside the Milky Way galaxy. Every single star you can see with your naked eye belongs to our galactic family. When you look up at that misty band of light, you're actually peering sideways through the disk of our galaxy, seeing the combined light of billions of distant stars, too faint to make out individually. You're looking at home from the inside out. But here's something that will completely change how you think about your place in the cosmos. Our galaxy is so vast, so incredibly immense, that if you could somehow shrink the entire Earth down to the size of a single grain of sand, the Milky Way would still be larger than the United States. We're not just small, we're incomprehensibly, beautifully, impossibly small within this cosmic structure we call home. The Milky Way spans roughly 100,000 light years from edge to edge. That means if you could travel at the speed of light, the fastest speed possible in our universe, it would take you 100,000 years to cross from one side of our galaxy to the other. Light that left the far edge of our galaxy when the first modern humans were just beginning to spread across Earth is only just now reaching the opposite edge. But size isn't the only thing that makes our galaxy extraordinary. The Milky Way contains somewhere between 100 billion and 400 billion stars. Think about that number for a moment. If you tried to count every star in our galaxy, counting one star per second without ever stopping to rest, it would take you more than 3,000 years to count them all. And that's just the stars we know about. Each of those stars is a sun potentially warming its own family of planets. Some of those stars are larger than our sun, some smaller. Some burn with the blue-white fire of youth. Others glow with the red warmth of old age. Some have already died spectacular deaths, leaving behind neutron stars or black holes. Others are just now being born in the stellar nurseries scattered throughout our galactic disk. Our sun sits about $26,000 light years from the center of the galaxy, roughly halfway between the galactic core and the outer edge. We're located in what astronomers call the Orion Arm, a minor spiral arm that branches off from one of the galaxy's major spiral structures. It's a comfortable suburban location in galactic terms, far enough from the crowded, chaotic center to avoid most cosmic catastrophes, but not so far out in the galactic countryside that we're isolated from the action. And we are in motion, constant, graceful, mind-bending motion. Our entire solar system is racing around the center of the galaxy at roughly 220 kilometers. That's about 490,000 mepri. In the time it takes you to read this sentence, we've traveled thousands of kilometers through space, carried along by the rotation of our galaxy. But even at that incredible speed, it takes our solar system approximately 225 million years to complete one full orbit around the galactic center. The last time we were at this exact position in our galactic orbit, dinosaurs ruled the Earth. The next time we return to this spot, who knows what wonders will have evolved on our little planet, if anything at all. Here's something that might surprise you. The Milky Way isn't alone in space. We're part of what astronomers call the Local Group, a collection of more than 80 galaxies bound together by gravity. Our nearest major galactic neighbor is the Andromeda Galaxy, located about 2.5 million light years away. That might sound impossibly distant, but in cosmic terms, Andromeda is practically next door. And here's something remarkable. Andromeda is heading straight toward us. Don't worry, this isn't something you need to add to your list of immediate concerns. The collision won't happen for another 4.5 billion years. When it does occur, it won't be the violent crash you might imagine. Instead, it will be a slow, graceful cosmic dance, lasting hundreds of millions of years, as the two galaxies merge into a single larger galaxy that astronomers have already nicknamed Milky. But long before that cosmic merger, our galaxy will undergo other dramatic changes. The Milky Way is constantly growing, constantly evolving. It's actively consuming smaller satellite galaxies that venture too close, like the Kind's major dwarf galaxy, which is currently being torn apart and absorbed by our galaxy's gravitational pull. This cosmic cannibalism has been happening for billions of years, and it's how galaxies like ours grow and evolve. At the heart of our galaxy lies something both fascinating and terrifying. Lurking at the galactic center, 26,000 light years away from us, is a supermassive black hole called Sagittarius, a star. This cosmic monster contains the mass of about 4 million suns, all compressed into a region smaller than our solar system. It's like having the mass of 4 million suns squeezed into a space that light takes only a few hours to cross. This black hole isn't just sitting there quietly. It's the gravitational anchor that holds our entire galaxy together. The cosmic engine around which hundreds of billions of stars dance their eternal waltz. Occasionally, gas and dust fall into this black hole, heating up to millions of degrees and creating brilliant flares of radiation that we can detect from our distant perch in the galaxy's suburbs. But perhaps the most mysterious aspect of our galaxy is what we can't see. astronomers have discovered that the stars in our galaxy are moving too fast. Based on the visible matter, we can observe the outer stars should be moving much more slowly than they actually are, or they should be flung out into intergalactic space. Something invisible is providing the extra gravitational pull needed to hold our galaxy together. We call this invisible component dark matter, and it makes up roughly 85% of all the matter in our galaxy. Think about that. Everything you can see, every star, every planet, every cloud of gas and dust represents only about 15% of what's actually there. The rest is made of something we can detect only through its gravitational effects, something that doesn't emit light or interact with ordinary matter in ways we can easily observe. Dark matter forms an enormous, invisible halo around our galaxy, extending far beyond the visible disk of stars. This invisible structure is what gives our galaxy its shape and stability. Without dark matter, the Milky Way as we know it simply couldn't exist. The stars would have dispersed long ago, leaving behind only isolated islands of matter drifting through the cosmic void. Our galaxy is also alive with ongoing star formation. In giant molecular clouds scattered throughout the galactic disk, new stars are being born all the time. These stellar nurseries, like the famous Eagle Nebula and Orion Nebula, are where gravity slowly pulls together clumps of gas and dust until they become dense enough and hot enough to ignite nuclear fusion. The process of star formation is both gentle and violent. It can take millions of years for a cloud of gas to slowly contract and form a new star. But when massive stars reach the end of their lives, they explode as supernovae, blasting heavy elements into space and triggering the formation of new generations of stars. These stellar explosions are essential for creating the chemical elements that make planets and life possible. Every element in your body heavier than hydrogen and helium was forged in the nuclear furnaces of ancient stars that lived and died before our sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created by stellar alchemy and scattered into space by dying stars. You are literally made of stardust, and that stardust carries within it the history of our galaxy. The Milky Way has spiral arms, beautiful curved structures that sweep through the galactic disk like frozen waves. These aren't permanent features like the arms of a pinwheel. Instead, they're density waves regions where stars and gas temporarily bunch up as they orbit the galactic center. As material moves through these density waves, it gets compressed, triggering new episodes of star formation that light up the spiral arms with the blue glow of young hot stars. Our solar system periodically passes through these spiral arms during our long journey around the galaxy. Some scientists have suggested that these passages might influence life on Earth by exposing our planet to increased cosmic radiation or by triggering climate changes. The connections between galactic structure and terrestrial life remain an active area of research, reminding us that we're not isolated from the cosmic environment that surrounds us. The Milky Way is also surrounded by a family of smaller satellite galaxies. The most famous of these are the large and small melanic clouds, visible from the southern hemisphere as fuzzy patches of light that early explorers mistook for pieces of the Milky Way that had broken off. These dwarf galaxies are slowly being stretched and distorted by our galaxy's gravity. creating streams of stars and gas that spiral into the Milky Way. As we continue our cosmic journey, we'll discover even more extraordinary facts about our galactic home. We'll explore the mysterious galactic center, investigate the possibility of other civilizations among the stars, and uncover the surprising ways that our galaxy connects to the larger cosmic web that spans the entire observable universe. The center of our galaxy holds secrets that would make the greatest mystery writers envious. Hidden behind thick clouds of dust and gas that block visible light, the galactic core is a realm of extremes where physics operates at its most dramatic limits, using infrared and radio telescopes that can peer through the cosmic dust. Astronomers have discovered a region unlike anywhere else in our galaxy. Near the supermassive black hole at our galactic center, stars orbit at speeds that defy imagination. Some of these stars complete their elliptical dance around Sagittarius A star in just 16 years, reaching velocities of up to 5,000 kilometers at their closest approach. That's more than 1% the speed of light. These stellar race cars experience gravitational forces so intense that Einstein's theories of relativity become essential for predicting their paths. But the galactic center isn't just home to our resident black hole. It's a stellar metropolis packed with stars at densities 1,000,000 times greater than in our quiet galactic suburb. If Earth orbited a star in the galactic center instead of our sun, the night sky would be illuminated by thousands of stars brighter than the full moon. There would be no true darkness, only an eternal twilight painted by the light of countless nearby suns. This crowded stellar environment creates cosmic fireworks on a regular basis. When stars venture too close to the central black hole, they can be torn apart by tidal forces in a process astronomers call spaghettification. The star gets stretched like taffy, with its material forming a bright accretion disk that spirals into the black hole while releasing tremendous amounts of energy. These stellar death throes can outshine entire galaxies for brief periods. The galactic center also harbors massive clouds of alcohol. Yes, you heard that correctly. Ethyl alcohol, the same molecule found in alcoholic beverages, exists in vast quantities near the center of our galaxy. One particular cloud contains enough alcohol to fill 400 trillion pints of beer. Of course, this cosmic cocktail also contains other less appetizing ingredients, like formaldehyde and cyanide, so it's definitely not suitable for consumption. These molecular clouds tell us something important about the chemistry of our galaxy. The space between stars isn't empty at all. It's filled with a thin but complex mixture of gas and dust that serves as the raw material for future generations of stars and planets. This interstellar medium contains over 200 different types of molecules, from simple water and carbon monoxide to complex organic compounds that might be precursors to life. Speaking of life, one of the most profound questions about our galaxy is whether we're alone among the stars. The Milky Way contains hundreds of billions of stars, and recent discoveries suggest that planets are incredibly common throughout the galaxy. Nearly every star appears to host at least one planet, and many of these worlds orbit within their star's habitable zone, where liquid water could exist on the surface. This means our galaxy likely contains billions of potentially habitable worlds. Some of these planets are probably very similar to Earth, with rocky surfaces, protective atmospheres, and oceans of liquid water. Others might be habitable in ways we're only beginning to imagine. Perhaps as moons orbiting giant planets, or as worlds where life thrives in underground oceans beneath frozen surfaces. The search for extraterrestrial intelligence has focused much of its attention on our galactic neighborhood. If advanced civilizations exist elsewhere in the Milky Way, they might be detectable through their radio transmissions, their modification of their local stellar environment, or other technological signatures. The famous Drake equation attempts to estimate how many communicating civilizations might exist in our galaxy, with estimates ranging from 1 US to thousands or even millions. But even if we never detect signals from alien civilizations, the sheer number of potentially habitable worlds in our galaxy suggests that life might be far more common than we once thought. Every time we discover a new exoplanet, every time we find life thriving in extreme environments on Earth, the possibility that our galaxy teems with biology becomes more compelling. The structure of our galaxy also tells a story of cosmic evolution spanning billions of years. The Milky Way wasn't always the elegant spiral we see today. In its youth, our galaxy was smaller, more chaotic, and actively growing through mergers with other galaxies. The oldest stars in our galaxy, found in the spherical halo that surrounds the galactic disk, are nearly as old as the universe itself, dating back more than 13 billion years. These ancient stars are like fossil remnants of our galaxy's violent past. They formed when the universe was much younger and contained far fewer heavy elements than today. Their chemical composition tells us about conditions in the early cosmos when the first generations of stars were just beginning to enrich the universe with elements heavier than hydrogen and helium. The galactic disk where we live is much younger, only about 8 to 10 billion years old. This is where most of the galaxy's star formation happens today, in a thin layer that's remarkably flat compared to the galaxy's overall size. If you scaled the Milky Way down to the size of a dinner plate, the disk would be only as thick as a sheet of paper. Within this disk, our galaxy maintains a delicate balance. New stars form from collapsing clouds of gas and dust, while older stars return material to space through stellar winds and supernova explosions. This cosmic recycling program has been operating for billions of years, gradually enriching the galaxy with heavier elements and making planets like Earth possible. The metallicity of stars, their abundance of elements heavier than hydrogen and helium, increases toward the center of the galaxy and decreases toward the outer edges. This gradient reflects the history of star formation and element production throughout our galactic home. Stars like our Sun, with their moderate metal content, occupy a sweet spot in the galactic disk where conditions are just right for the formation of rocky planets and potentially complex chemistry. Our galaxy also experiences seasons of sorts, though they last for hundreds of millions of years. As we orbit the galactic center, we periodically pass through the spiral arms regions of increased density where star formation is more active and massive stars explode more frequently. These passages might influence the rate of cosmic ray bombardment reaching Earth, potentially affecting climate and evolution over geological timescales. The Milky Way is also part of larger cosmic structures that extend far beyond our galaxy's boundaries. We exist within the local group of galaxies, which in turn belongs to the Virgo supercluster, a vast collection of galaxy groups and clusters stretching across 110 million light-year. This supercluster is itself part of an even larger structure called Ionia, which contains over 100,000 galaxies. These nested hierarchies of cosmic structure remind us that our galaxy, vast as it is, represents just one small part of an even grander cosmic web. Dark matter filaments connect galaxies across billions of light years, creating a scaffolding upon which the visible universe is built. The Milky Way follows the gravitational flows within this cosmic web, slowly moving through space at hundreds of kilometers relative to the cosmic microwave background radiation. But perhaps the most remarkable thing about our galaxy is that it has remained stable enough, long enough for complexity to emerge. The Milky Way has avoided major disruptions for billions of years, allowing successive generations of stars to form, live, and die. This stability has permitted the gradual accumulation of heavy elements necessary for rocky planets and ultimately for life itself. We exist during a special time in our galaxy's history when star formation continues at a steady pace but hasn't yet exhausted the supply of raw materials. In the far future, the Milky Way will gradually consume its remaining gas and dust, and star formation will slow to a trickle. The galaxy will grow dimmer and redder as massive bright stars burn out and are not replaced. But that future lies trillions of years in the distance. For now, our galaxy continues its ancient dance, spiral arms slowly rotating, new stars igniting in stellar nurseries, and the great wheel of the Milky Way carrying us all on a journey through space and time that connects us to the deepest mysteries of the cosmos. As you drift deeper into contemplation of our galactic home, consider this extraordinary fact that will forever change how you think about your cosmic address. The Milky Way isn't just sitting peacefully in space, slowly rotating like some celestial pinwheel. Our entire galaxy is hurtling through the universe at an almost incomprehensible speed of 600 km/s. That's over 1.3 million miles an hour. Think about that for a moment. As you rest there, feeling perfectly still, you're actually racing through the cosmos faster than anything humans have ever built could dream of traveling. In the time it takes you to take a single breath, our entire galaxy, with all its hundreds of billions of stars, has moved thousands of kilometers through space. We're all passengers on this cosmic express, and we don't even feel the motion. But where are we going? Our galaxy, along with the rest of the local group, is being pulled towards something called the Great Attractor, a massive gravitational anomaly located about 250 million light-year away. This cosmic magnet is so powerful that it's tugging thousands of galaxies toward it, including our own. We're part of a vast river of galaxies flowing through space, all following the invisible currents of dark matter that shape the large-scale structure of the universe. The story becomes even more fascinating when we consider the shape of our galaxy itself. From our vantage point inside the Milky Way, It took centuries of careful observation for astronomers to piece together what our galaxy actually looks like. We're rather like bacteria living on a dinner plate, trying to figure out the plate's overall shape and size. For the longest time, we thought we lived in a perfectly flat spiral galaxy, elegant and symmetrical. But recent discoveries have revealed something far more interesting. Our galaxy is warped. The outer edges of the Milky Way's disk don't lie in a flat plane, but instead twist and bend like the brim of a hat that's been sat on. This cosmic warping might be caused by the gravitational influence of our satellite galaxies, particularly the large and small melanic clouds, which are slowly distorting our galaxy's shape as they orbit around us. Even more remarkably, our galaxy has a heartbeat. Well, not exactly a heartbeat, but something almost as rhythmic and mysterious. The Milky Way experiences what astronomers call galactic oscillations. As our galaxy moves through space, it bounces up and down relative to the plane of nearby galaxies with a period of roughly 60 million years. These cosmic oscillations might influence the rate at which comets from the outer solar system are disturbed and sent careening toward the inner planets. Some scientists have proposed that these galactic oscillations might be connected to mass extinction events on Earth. The idea is that as our solar system bobs up and down through the galactic plane, we encounter different densities of dark matter and different intensities of cosmic radiation. While this connection remains highly speculative, it's a fascinating reminder that our planet's history might be intimately connected to our galaxy's motion through space. The Milky Way also contains structures that challenge our understanding of how galaxies form and evolve. Astronomers have discovered vast streams of stars stretching across the sky, remnants of smaller galaxies that our Milky Way has consumed over billions of years. These stellar streams are like cosmic fossils preserving evidence of ancient galactic collisions and mergers that shaped our galaxy's current form. One of the most spectacular of these streams is called the Sagittarius Stream, created by the ongoing destruction of the Sagittarius dwarf galaxy. This unfortunate small galaxy has been making repeated passes through our galaxy for billions of years. And each time it does, our Milky Way's gravity strips away more of its stars. What remains is a long trail of stars wrapping completely around our galaxy, visible as a faint river of light to those who know where to look. These cosmic archaeological discoveries tell us that galaxy formation is messier and more violent than we once imagined. Galaxies don't simply form in isolation and then remain unchanged. They grow by consuming their neighbors, and they bear the scars of these ancient battles written in streams of displaced stars. Our galaxy is a cosmic graveyard filled with the remains of dozens of smaller galaxies that made the mistake of wandering too close to our gravitational embrace. But perhaps the most mind-bending aspect of our galaxy concerns what lies beyond its visible boundaries. The stars and gas that we can see represent only a tiny fraction of the Milky Way's total mass. The rest consists of that mysterious dark matter we mentioned earlier, forming an enormous invisible halo that extends perhaps 10 times farther from the galactic center than the visible stars. This dark matter halo isn't uniform or smooth. Computer simulations suggest it's filled with substructure, smaller clumps and streams of dark matter left over from the formation of our galaxy. Some of these dark matter subhalos might be the remains of ancient dwarf galaxies that were completely stripped of their visible stars, leaving behind only their invisible dark matter cores as ghostly reminders of their former existence. Even stranger, our galaxy might be surrounded by a vast atmosphere of hot ionized gas, extending hundreds of thousands of light years into space. This galactic corona, as it's called, contains as much mass as all the stars in the galaxy combined, but it's so diffuse and hot that it's nearly impossible to detect directly. Think of it as our galaxy's extended atmosphere, a tenuous envelope of gas that connects us to the intergalactic medium. The temperature of this galactic atmosphere is truly extraordinary, reaching millions of degrees. That's hot enough to strip electrons from atoms, creating a plasma that glows faintly in X-ray light. This superheated gas might be the reservoir from which our galaxy draws new material for continued star formation, slowly cooling and condensing over millions of years to become the raw material for future generations of stars. Within our galaxy's disk, the distribution of different types of stars tells a story of cosmic evolution spanning billions of years. The oldest stars, formed when our galaxy was young, are metal poor and tend to have highly elliptical orbits that carry them far from the galactic plane. These stellar senior citizens are like time capsules, preserving information about conditions in the early universe when heavy elements were rare. Younger stars like our Sun are metal-rich and tend to follow more circular orbits within the galactic disk. They formed from gas that had been enriched by previous generations of stars, gas that contained the carbon, oxygen, silicon, and iron necessary to build rocky planets. The chemical evolution of our galaxy has been a gradual process, with each stellar generation leaving behind a legacy of heavier elements for their successors. This chemical gradient throughout our galaxy has profound implications for the potential for life. Stars in the outer regions of the galaxy, where heavy elements are scarce, are less likely to host rocky planets like Earth. Stars too close to the galactic center face different challenges, including intense radiation from the central black hole and frequent gravitational disturbances from nearby stars. Our Sun occupies what some astronomers call the galactic habitable zone, the region where conditions are just right for stable planetary systems and potentially complex chemistry. The magnetic field of our galaxy adds another layer of complexity to this cosmic story. The Milky Way possesses a weak but extensive magnetic field that permeates the space between stars. This galactic magnetic field helps regulate star formation by supporting gas clouds against gravitational collapse and by guiding the flow of charged particles throughout the galaxy. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events, follow the twisted paths of this magnetic field as they journey across the galaxy. Some of these cosmic rays eventually reach Earth, where they can affect our atmosphere and potentially influence the evolution of life. The galactic magnetic field acts like a cosmic highway system, channeling these energetic particles along specific routes through space. The strength and structure of our galaxy's magnetic field also influence how gas moves within the galactic disk. Magnetic forces can drive gas inward toward the galactic center or outward toward the galaxy's edges, affecting where new stars form and how quickly our galaxy consumes its fuel for continued star formation. Understanding these magnetic processes is crucial for predicting the future evolution of our galactic home. Recent observations have revealed that our galaxy experiences what astronomers call galactic fountains. Hot gas, heated by supernova explosions and stellar winds, rises from the galactic disk like water from a fountain, reaching heights of thousands of light years before cooling and falling back down. This galactic circulation helps mix heavy elements throughout the galaxy and may play a crucial role in regulating the rate of star formation. These galactic fountains create a complex three-dimensional structure within our galaxy that's far more dynamic than the simple flat disk we once imagined. Gas flows up and down, in and out, creating circulation patterns that connect the galactic disk to the extended halo of hot gas that surrounds our galaxy. We live within a cosmic weather system of incredible complexity and beauty. As we continue our gentle drift through the facts about our galactic home, we begin to appreciate that the Milky Way isn't just a collection of stars scattered through space. It's a living, breathing, evolving system where every component influences every other component in an intricate cosmic dance that has been unfolding for over 13 billion years. And somehow, impossibly wonderfully, we find ourselves part of this magnificent story, conscious beings made of stellar material, contemplating the very galaxy that gave us birth. The history of our galaxy is written in the stars themselves, and if you know how to read the celestial language, the Milky Way reveals a story more epic than any human mythology. Every star carries within its spectrum the fingerprints of its birth, the chemical composition that tells us when and where it formed. The oldest stars in our galaxy are like ancient libraries preserving information about the universe when it was young, dark, and almost entirely composed of hydrogen and helium. These stellar elders, some nearly as old as the universe itself, formed from pristine gas that had never been touched by stellar alchemy. They shine with a different light than younger stars lacking the heavy elements that give color and complexity to stellar spectra. When you look at these ancient suns, you're seeing light that began its journey when the cosmos was still finding its rhythm, when galaxies were smaller and more chaotic than they are today. But our galaxy hasn't remained frozen in time. It's been growing, learning, evolving for billions of years. Through a process that astronomers call chemical evolution, each generation of stars has enriched the galaxy with new elements, creating the cosmic periodic table that makes complexity possible. The iron in your blood was forged in a supernova explosion that lit up the galaxy long before our sun was born. The calcium in your bones was created in the nuclear furnaces of massive stars that lived fast and died young, scattering their stellar ashes into the cosmic wind. This process of stellar death and rebirth has been happening throughout our galaxy for eons, but it's not uniform everywhere. The inner regions of the Milky Way, closer to the galactic center, experienced more intense star formation in the past. They're like cosmic cities, where generations of stars lived, died, and left behind their chemical legacies. The outer regions are more like stellar suburbs, where star formation has been more leisurely and the chemical enrichment process has taken longer. Our solar system formed in what astronomers call the thin disk of our galaxy, a region where multiple generations of stars have lived and died, creating the perfect chemical mixture for rocky planets and complex chemistry. We exist in a kind of galactic Goldilocks zone, not too close to the violent center, not too far from the action in the outer reaches, but just right for the emergence of worlds like Earth. The timing of our arrival in this cosmic story is also remarkably fortunate. We exist during what some astronomers call the stellar prime time of our galaxy, when star formation is still active, but has settled into a steady rhythm. Billions of years from now, the Milky Way will begin to run out of the raw materials needed to make new stars. The galaxy will gradually fade as the most massive, brightest stars burn out and are not replaced. But that twilight is still incredibly distant in the future. For now, our galaxy continues to surprise us with its complexity and beauty. Astronomers have discovered that the Milky Way contains structures called stellar nurseries, vast clouds of gas and dust where new stars are constantly being born. These cosmic maternity wards are some of the most beautiful objects in our galaxy, glowing with the light of young hot stars and painted in brilliant colors by the fluorescence of heated gas. The Eagle Nebula, the Orion Nebula, the Carina Nebula. These are the places where our galaxy is actively creating its future. Within these stellar nurseries, gravity slowly gathers material together, compressing gas and dust until it becomes hot enough to ignite nuclear fusion. It's a process that can take millions of years, but when it's complete, a new star joins the galactic community, adding its light to the cosmic tapestry. But star formation isn't just a gentle process of gravitational collapse. It's also influenced by shock waves from supernova explosions, stellar winds from massive stars, and the complex interplay of magnetic fields threading through the interstellar medium. These forces can trigger star formation in some regions while suppressing it in others, creating the patchy, irregular distribution of stellar nurseries we observe throughout our galaxy. The most massive stars in these nurseries burn bright and die young, exploding as supernova after only a few million years of life. These stellar explosions are among the most energetic events in our galaxy, briefly outshining billions of ordinary stars and creating expanding bubbles of hot gas that can influence star formation across hundreds of light years. The shock waves from these explosions compress nearby gas clouds, potentially triggering the birth of new stellar generations. This cycle of stellar birth life and death has been sculpting our galaxy for billions of years, creating the complex structure we see today. The spiral arms of the Milky Way are outlined by these stellar nurseries and the bright young stars they produce. As we orbit the galaxy, our solar system occasionally passes through these spiral arms, experiencing brief periods of increased radiation from nearby massive stars and supernova explosions. Some scientists have speculated that these passages through spiral arms might have influenced the evolution of life on Earth, potentially triggering ice ages or mass extinctions through increased cosmic ray bombardment. While the evidence for such connections remains debatable, it's a fascinating reminder that Earth's history has been shaped not just by terrestrial processes, but by our journey through the galaxy itself. The structure of our galaxy also reveals something profound about the nature of matter and energy in the universe. The beautiful spiral pattern that defines the Milky Way isn't permanent, like the arms of a pinwheel. Instead, it's what astronomers call a density wave, a pattern that moves through the galactic disk, like a wave through water. Material flows into the spiral arms, gets compressed, forms new stars, and then flows back out, while the pattern itself persists and slowly rotates around the galaxy. This discovery revolutionized our understanding of galactic structure. Spiral arms aren't rigid features that rotate with the galaxy like spokes on a wheel. They're dynamic patterns maintained by the collective gravitational influence of all the stars and gas in the galactic disk. It's as if our galaxy is a cosmic musical instrument, with a spiral pattern representing standing waves in the distribution of matter and energy. The mathematics describing these density waves is remarkably similar to the equations that describe waves in other physical systems, from sound waves in air to quantum mechanical wave functions. This deep mathematical connection suggests that spiral patterns might be a natural consequence of how matter behaves when it's distributed in rotating gravitating systems like galaxies. Our galaxy also participates in a cosmic ecosystem that extends far beyond its visible boundaries. The space between galaxies isn't empty, but is filled with a tenuous gas called the intergalactic medium. This cosmic web of gas connects galaxies across millions of light years, providing the raw material for continued galactic growth and evolution. The Milky Way is constantly accreting material from this intergalactic medium, slowly growing in mass as it captures gas from the cosmic web. At the same time, stellar winds and supernova explosions drive gas out of our galaxy, enriching the intergalactic medium with heavy elements created by stellar nucleosynthesis. Our galaxy breathes, inhaling pristine hydrogen and helium from space, while exhaling processed material enriched with the products of stellar evolution. This galactic breathing process operates on timescales of hundreds of millions of years, far longer than human civilization, but rapid compared to the age of the universe. It's one of the ways that galaxies like ours maintain their ability to form new stars over billions of years, despite the fact that star formation should eventually consume all available gas. The study of our galaxy has also revealed the existence of hypervelocity stars, stellar outcasts that have been ejected from the Milky Way at speeds high enough to escape our galaxy's gravitational pull entirely. These stellar refugees are thought to be created when binary star systems venture too close to the supermassive black hole at our galaxy's center. The intense gravitational field disrupts the binary, sending one star plunging into the black hole, while launching its companion into intergalactic space at thousands of kilometers. These hypervelocity stars carry with them information about the extreme environment near our galaxy's central black hole. By studying their properties and trajectories, astronomers can learn about processes occurring in one of the most exotic regions of our galaxy, a place where Einstein's general relativity is essential for understanding the motion of matter and energy. The discovery of hypervelocity stars also raises intriguing questions about the connectivity between galaxies. If our galaxy can eject stars into intergalactic space, presumably other galaxies can do the same. This means there might be a population of intergalactic stars, homeless suns wandering through the cosmic void between galaxies. Some of these stellar nomads might even host planetary systems, creating the possibility of truly isolated worlds drifting through the darkness between galactic communities. Recent advances in astronomical technology have allowed us to peer deeper into our galaxy than ever before, revealing structures and processes that were completely unknown just a few decades ago. Infrared telescopes can see through the dust that obscures our view of the galactic center, revealing the chaotic environment surrounding our galaxy's central black hole. Radio telescopes can detect the faint emissions from cold gas clouds where future stars will be born. Perhaps most remarkably, we can now detect gravitational waves, ripples in space, time itself created by the most violent events in our galaxy. When two black holes spiral into each other and merge, they create gravitational waves that propagate across the galaxy at the speed of light. These cosmic tremors carry information about events so extreme that they were completely inaccessible to traditional astronomy. The detection of gravitational waves has opened an entirely new window into our galaxy's most energetic phenomena. We can now study black hole merges, neutron star collisions, and potentially other exotic events that produce no light but create detectable distortions in the fabric of space-time. It's as if we've developed a new sense, allowing us to feel the vibrations of cosmic events happening thousands of light years away. This gravitational wave astronomy has already revealed that our galaxy contains more black holes than we previously suspected. Many of these black holes are the remnants of massive stars that lived and died in previous epochs of our galaxy's history. They're invisible to optical telescopes, but announce their presence when they merge with other black holes, creating gravitational wave signals that we can detect with extraordinary precision. The story of our galaxy is still being written, and we're privileged to witness this ongoing cosmic narrative. New stars are being born in stellar nurseries, scattered throughout the galactic disk. Old stars are dying in spectacular supernova explosions that briefly outshine entire galaxies. Our galaxy continues its ancient dance, with its satellite galaxies slowly consuming some while being influenced by others. As you rest here, contemplating these cosmic truths, remember that you're not just an observer of this galactic story, you're a participant in it. The atoms in your body were created in the nuclear furnaces of stars that lived and died billions of years ago. The energy that powers your thoughts comes from fusion reactions in our sun, which is itself just one star among hundreds of billions in our galactic community. Every breath you take contains atoms that have been recycled through countless stellar generations, each one carrying within it the history of our galaxy's chemical evolution. You are made of processed stellar material, assembled into the temporary but remarkable pattern we call human consciousness. In a very real sense, you are the galaxy becoming aware of itself, a way for the Milky Way to contemplate its own existence through the evolved complexity of biological intelligence. The vastness of our galaxy can make us feel small and insignificant, but it can also fill us with wonder at being part of something so magnificent and ancient. We exist during a brief moment in our galaxy's history when stars still shine brightly, when planets can form and evolve complex chemistry, when the universe is still young enough for consciousness to emerge and ask questions about its own origins. The spiral arms of our galaxy aren't just beautiful cosmic decorations. They're active regions where the drama of stellar life plays out on a scale that dwarfs human imagination. As our solar system continues its leisurely 225 million year orbit around the galactic center, we periodically encounter these spiral arms like a ship crossing ocean currents in the cosmic sea. When we pass through a spiral arm, we enter regions where the density of stars, gas, and dust increases dramatically. These are the galaxy's most vibrant neighborhoods, where massive blue giants burn with the intensity of a million suns, illuminating vast clouds of hydrogen gas in brilliant reds and pinks. But these stellar giants live fast and die young, exploding a supernova after only a few million years, their deaths triggering waves of new star formation throughout the surrounding region. The shock waves from these stellar explosions propagate through space like ripples on a pond, compressing nearby gas clouds and triggering the collapse that leads to new stellar births. It's a cosmic chain reaction that has been occurring throughout our galaxy's history, with each generation of massive stars sacrificing themselves to kindle the next generation. This stellar recycling program has been operating for billions of years, gradually transforming our galaxy from a simple collection of hydrogen and helium into the complex, chemically rich environment we inhabit today. But our galaxy harbors secrets that challenge everything we thought we knew about cosmic evolution. Hidden within the galactic disk are what astronomers call moving groups, collections of stars that share common motion through space, despite being separated by hundreds of light years. These stellar associations are the scattered remnants of ancient star clusters that formed together but have since been dispersed by the galaxy's gravitational tides. Some of these moving groups contain stars that are chemically identical, sharing precisely the same abundances of heavy elements despite being spread across vast distances. It's as if someone took a stellar family and scattered its members throughout the galaxy while preserving their genetic fingerprints in the form of identical chemical compositions. These dispersed stellar families tell us that our galaxy's structure has been shaped by processes far more complex than simple orbital mechanics. The discovery of these moving groups has revolutionized our understanding of stellar formation and galactic evolution. Stars don't just form in isolation and then follow independent paths through the galaxy. They're born in clusters live together for millions of years and then slowly drift apart as galactic tides and gravitational interactions reshape their orbits. Our own sun might have siblings scattered throughout the galaxy, stars that formed from the same molecular cloud 4.6 billion years ago, but have since wandered far from their birthplace. Finding our sun's lost siblings has become one of the holy grails of modern astronomy. By analyzing the chemical compositions and orbital properties of nearby stars, astronomers are searching for stars that share our sun's unique stellar fingerprint. Several candidate solar siblings have been identified, stars with compositions and ages that suggest they might have formed in the same stellar nursery as our Sun. If confirmed, these discoveries would provide unprecedented insights into the conditions that existed when our solar system was born. The galactic disk itself is far more complex than the simple flat structure we once imagined. Recent observations have revealed that the Milky Way's disk is actually composed of multiple components with different ages, chemical compositions, and kinematic properties. The thin disk where we live contains younger stars with circular orbits and high metal content. The thick disk contains older stars with more elliptical orbits and lower metal abundances, suggesting it formed during an earlier, more chaotic epoch of our galaxy's history. Between these two major disk components lies a population of intermediate age stars that bridge the gap between the old thick disk and the young thin disk. This intermediate population tells a story of gradual transition, suggesting that our galaxy's evolution wasn't marked by sudden dramatic changes, but by a slow, steady progression from chaos to the ordered structure we see today. The existence of these multiple disk components has profound implications for understanding how galaxies like ours form and evolve. It suggests that galactic assembly is a complex, multi-stage process that unfolds over billions of years. Early in our galaxy's history, star formation was more violent and chaotic, creating the thick disk population. As time passed and the galaxy settled into a more stable configuration, star formation became more organized, creating the thin disk where most current stellar birth occurs. This layered structure of our galaxy is like geological strata in Earth's crust, with each stellar population preserving information about the conditions that existed when it formed. By studying these stellar fossils, astronomers can reconstruct the history of our galaxy, much like paleontologists reconstruct Earth's history by studying layers of sedimentary rock. The chemical evolution of our galaxy tells an even more detailed story about cosmic history. The oldest stars in our galaxy contain almost no elements heavier than hydrogen and helium, reflecting the pristine composition of the early universe. These stellar ancients formed from gas that had never been processed through stellar cores, gas that retained the primordial composition established during the first few minutes after the Big Bang. As successive generations of stars lived and died, they gradually enriched the galaxy with heavier elements created through nuclear fusion in stellar cores and explosive nucleosynthesis during supernova events. This chemical enrichment wasn't uniform throughout the galaxy. The inner regions, where star formation was more intense, became enriched more rapidly than the outer regions, creating gradients in chemical composition that persists to this day. These chemical gradients have important consequences for planet formation and the potential for life. Rocky planets like Earth can only form in regions where sufficient quantities of heavy elements are available. The outer regions of our galaxy, where heavy elements remain scarce, are less likely to host terrestrial planets capable of supporting complex life chemistry and potentially life. Our Sun's location in the galactic disk places us in what some astronomers call the galactic habitable zone, the region where chemical abundances are just right for rocky planet formation, but not so high that planetary systems become unstable due to frequent gravitational perturbations from nearby stars. It's another example of the remarkable fine-tuning that has made our existence possible. The study of our galaxy has also revealed the existence of stellar streams, vast rivers of stars stretching across the sky that mark the tidal disruption of satellite galaxies and globular clusters. These stellar streams are like cosmic contrails, marking the paths that smaller stellar systems have taken as they orbit through our galaxy's gravitational field. The most spectacular of these streams is the Sagittarius stream, created by the ongoing tidal disruption of the Sagittarius dwarf elliptical galaxy. This unfortunate small galaxy has been making repeated passages through our galaxy for billions of years, and each time it does, our galaxy's powerful tidal forces strip away more of its stars. What remains is a long trail of stars that wraps completely around our galaxy, creating a vast stellar ring that's slowly being absorbed into the Milky Way structure. These tidal streams provide direct evidence that galaxies grow by consuming their smaller neighbors, a process that has been central to galactic evolution throughout cosmic history. Our galaxy bears the scars of dozens of such cannibalistic encounters, each one leaving behind streams of displaced stars that mark ancient acts of cosmic consumption. The detection and mapping of these stellar streams has become one of the most active areas of galactic astronomy. Each newly discovered stream tells us about a satellite galaxy or globular cluster that our galaxy has destroyed, adding another piece to the puzzle of how the Milky Way assembled its current mass and structure. But perhaps the most mysterious aspect of these stellar streams is what they tell us about dark matter. The stars and tidal streams follow paths determined not just by our galaxy's visible matter, but by the distribution of invisible dark matter as well. By carefully measuring the motions of stars in these streams, astronomers can map the dark matter halo that surrounds our galaxy, revealing the invisible scaffolding that holds our galactic home together. These measurements have revealed that our galaxy's dark matter halo is far more complex than simple theoretical models suggested. Rather than being smooth and spherical, the dark matter halo appears to be filled with substructure clumps and streams of dark matter that reflect our galaxy's violent assembly history. Some of these dark matter clumps might be the remnants of ancient satellite galaxies that were completely stripped of their stars, leaving behind only their invisible dark matter cores. The realization that our galaxy is embedded within this vast, complex halo of dark matter has fundamentally changed how we think about galactic structure and evolution. The visible stars and gas that we can observe directly represent only the tip of the iceberg. The bulk of our galaxy's mass consists of mysterious dark matter that we can detect only through its gravitational effects. This dark matter halo extends far beyond the visible disk of our galaxy, perhaps 10 times farther from the galactic center than the most distant stars we can observe. We live within this invisible ocean of dark matter, and it flows through our solar system and even through our bodies without our being aware of its presence. Every second, billions of dark matter particles pass through every cubic cm of a space, including the space occupied by your body, without interacting with ordinary matter in any detectable way. The nature of dark matter remains one of the greatest unsolved mysteries in astronomy and physics. We know it exists because of its gravitational effects on visible matter, but we have no idea what it's made of. Dozens of experiments around the world are trying to detect dark matter particles directly, but so far, this mysterious substance has eluded all attempts at direct detection. Some of the most sensitive experiments ever built are buried deep underground in mines and mountains, shielded from cosmic rays and other sources of background radiation. These detectors are designed to register the tiny energy deposits that would be created if a dark matter particle occasionally collides with an ordinary atom. Despite years of searching with ever more sensitive instruments, dark matter particles have remained frustratingly elusive. The failure to detect dark matter directly has led some scientists to propose alternative theories that modify our understanding of gravity rather than invoking invisible matter. These modified gravity theories suggest that the gravitational force might behave differently on galactic scales than it does in our solar system, eliminating the need for dark matter to explain galactic rotation curves and other observations. However, the overwhelming majority of evidence continues to favor the existence of dark matter over modified gravity theories. The cosmic microwave background radiation, the large-scale structure of the universe, and the behavior of galaxy clusters all point to the existence of invisible matter that interacts gravitationally but not electromagnetically. The mystery of dark matter reminds us how much we still don't know about our cosmic home. Despite centuries of astronomical observation and decades of sophisticated space-based telescopes, the majority of our galaxy's mass remains completely mysterious to us. We're like explorers mapping a vast continent while being aware that most of the terrain remains hidden from our view. This humbling realization adds a sense of wonder and mystery to our contemplation of the galaxy. The Milky Way isn't just the collection of stars and gas that we can observe. It's a vast, complex system dominated by forces and materials that we're only beginning to understand. Every new discovery raises as many questions as it answers, reminding us that the universe is far stranger and more complex than our everyday experience would suggest. As our journey through galactic facts continues, we begin to appreciate that the Milky Way isn't just our cosmic address. It's a dynamic, evolving system that has been shaped by billions of years of complex physical processes, from the nuclear fusion occurring in stellar cores to the gravitational interactions between dark matter clumps, from the shock waves of supernova explosions to the slow, patient accumulation of heavy elements. Our galaxy is a masterpiece of cosmic engineering that continues to surprise and delight those who study it. The story of our galaxy is ultimately the story of how simple hydrogen and helium, the primordial elements created in the Big Bang, have been transformed through stellar alchemy into the rich, complex chemical mixture that makes planets and life possible. It's a story of emergence and complexity, of how gravity and nuclear physics have conspired to create structures of breathtaking beauty and mind-bending scale. And perhaps most remarkably, it's a story that has produced observers capable of contemplating their own cosmic origins. We are made of processed stellar material, assembled into temporary but remarkable patterns, capable of consciousness, curiosity, and wonder. In studying our galaxy, we're not just learning about distant astronomical objects, we're discovering our own cosmic heritage, tracing the long chain of physical and chemical evolution that connects us to the first stars that lit up the early universe. The Milky Way has given birth to us, nurtured us, and provided the stable cosmic environment necessary for the emergence of complex chemistry and biology. In return, we've developed the capacity to study our galactic home, to map its structure, to understand its history, and to appreciate its beauty. We are the galaxy's gift to itself, a way for cosmic matter to become self-aware and to contemplate the magnificent story of which we are all a part. Perhaps the most extraordinary discovery about our galaxy in recent years concerns something called the Fermi bubbles, massive structures extending 50,000 light years above and below the galactic plane. These enormous balloon-like regions of high-energy gas were completely unknown until detected by the Fermi Gamma Ray Space Telescope in 2010. The bubbles emit gamma rays, the most energetic form of light in the universe, suggesting they were created by some tremendously powerful event in our galaxy's past. These cosmic bubbles dwarf anything else in our galaxy. If you could somehow see them with your naked eyes, they would appear 200 times larger than the full moon in our night sky. The energy required to create such structures is almost incomprehensible, equivalent to the explosion of millions of supernovae. Yet somehow, our galaxy managed to blow these enormous bubbles of superheated gas into the space above and below its disk. The leading theory is that these bubbles were created by past activity from the supermassive black hole at our galaxy's center. Sagittarius AAR wasn't always the relatively quiet giant we observe today. In the past, it may have been actively feeding on surrounding gas and matter, creating powerful jets of energy that carved out these vast caverns in the galactic halo. It's as if our galaxy experienced a period of cosmic indigestion, burping out these enormous structures that still glow with residual energy millions of years later. The discovery of the Fermi bubbles has revolutionized our understanding of how galaxies interact with their surrounding environment. These structures suggest that galaxies aren't isolated islands of stars floating in empty space. Instead, they're dynamic systems that can dramatically influence the space around them, creating structures that extend far beyond their visible boundaries. But the Fermi bubbles aren't the only surprises hiding in our galactic neighborhood. Astronomers have also discovered what they call high-velocity clouds, massive clumps of hydrogen gas racing through space at hundreds of kilometers. These cosmic nomads don't follow the orderly rotation of our galaxy's disk, but instead plunge through the galactic halo on highly elongated orbits. Some of these high-velocity clouds are thought to be pristine gas left over from the formation of our galaxy, material that somehow avoided being incorporated into the galactic disk billions of years ago. Others might be the gaseous remnants of small satellite galaxies that were stripped of their stars, but retained some of their gas. A few, might even be intergalactic gas clouds falling into our galaxy for the first time, bringing fresh fuel for future star formation. One particularly intriguing high-velocity cloud is heading straight for our galaxy's disk and will collide with it in about 30 million years. This cosmic collision won't be violent in human terms, but it will compress gas in our galaxy's outer regions and likely trigger a burst of new star formation. It's a reminder that our galaxy continues to grow and evolve, accreting new material from its surroundings even today. The space between the stars in our galaxy, once thought to be empty, turns out to be filled with a complex ecosystem of gas dust and magnetic fields. This interstellar medium isn't uniform, but varies dramatically from region to region. Near hot young stars, the gas is ionized and glows with the characteristic colors of different elements. In the cold, dark regions between stars, gas can condense into molecular clouds, where temperatures drop to just a few degrees above absolute zero. These molecular clouds are among the coldest places in the universe, colder even than the cosmic microwave background radiation that fills all of space. Within these frigid environments, hydrogen atoms pair up to form molecules, and more complex chemistry becomes possible. Water, ammonia, methanol, and even ethyl alcohol have been detected in these interstellar clouds, creating vast cosmic distilleries floating between the stars. The dust grains mixed in with this interstellar gas play a crucial role in galactic chemistry. These microscopic particles, smaller than the wavelength of visible light, provide surfaces where atoms can stick together and form molecules. Without interstellar dust, the complex chemistry necessary for star and planet formation would be impossible. But this dust also makes our galaxy partially opaque, blocking our view of distant stars and creating the dark lanes visible in edge spiral galaxies. The dust preferentially absorbs blue light while allowing red light to pass through, causing distant stars to appear redder than they actually are. This interstellar Reening effect has to be carefully corrected when astronomers study distant objects within our galaxy. The magnetic fields threading through our galaxy create another layer of complexity in this interstellar environment. These fields, though incredibly weak by everyday standards, play important roles in regulating star formation and guiding the flow of charged particles throughout the galaxy. The galactic magnetic field acts like a cosmic infrastructure, channeling energy and matter along invisible highways that span thousands of light years. Cosmic rays, high energy particles accelerated by supernova explosions and other violent events, follow these magnetic field lines as they journey across the galaxy. Some of these cosmic rays eventually reach Earth, where they constantly bombard our atmosphere and create cascades of secondary particles that rain down on the surface. Every second, several cosmic ray particles pass through your body, ghostly messengers from distant stellar explosions, carrying energy that originated in the most violent events our galaxy has witnessed. The study of cosmic rays has revealed that our galaxy is a much more energetic place than visible light observations would suggest. Supernova explosions, pulsar winds, and the acceleration zones around black holes all contribute to a galaxy-wide population of high-energy particles that carry as much energy as the starlight itself. We live in a universe filled with invisible radiation, a testament to the violent processes that have shaped our cosmic home. Recent discoveries have also revealed that our galaxy contains much more antimatter than anyone expected. Antimatter, the exotic opposite of ordinary matter, annihilates instantly when it contacts regular matter, releasing tremendous amounts of energy. Despite this destructive property, astronomers have detected a fountain of antimatter rising from the galactic center, suggesting that some unknown process is continuously creating these exotic particles. The source of this galactic antimatter remains mysterious. It could be produced by the decay of dark matter particles, by the acceleration of particles around the central black hole, or by some other exotic process we haven't yet imagined. Whatever creates it, this antimatter fountain adds another layer of mystery to our galaxy's already complex structure. The rotation of our galaxy itself holds surprises that continue to puzzle astronomers. While we know that our solar system orbits the galactic center once every 225 million years, the pattern of rotation throughout the galaxy is far from simple. The inner regions rotate faster than the outer regions, but not in the way that simple physics would predict. This differential rotation creates spiral density waves that propagate through the galactic disk like ripples on a pond. These density waves aren't just mathematical curiosities. They have profound effects on the distribution of stars and gas throughout our galaxy. As material flows into a spiral arm, it gets compressed, triggering episodes of star formation that light up the arm with the blue glow of young massive stars. As the material flows back out of the arm, star formation subsides and the region returns to a more quiescent state. This process creates the beautiful spiral pattern that defines our galaxy's appearance. But it also means that the spiral arms we see today aren't the same structures that existed millions of years ago. The arms are like waves in the galactic disk, persistent patterns that maintain their shape even as individual stars and gas clouds flow through them. It's as if our galaxy is a cosmic musical instrument, with the spiral pattern representing standing waves in the distribution of matter and energy. The discovery that spiral arms are transient features rather than permanent structures has changed how we think about galactic evolution. Galaxies aren't static objects, but dynamic systems where patterns form, persist for a while, and then evolve into new configurations. The beautiful spiral galaxies we observe today will look different in the future as their spiral patterns wind up, fade away, or transform into new structures. Our galaxy's future is written in the motions we can observe today. Computer simulations that follow the gravitational interactions of billions of particles can predict how our galaxy will evolve over cosmic time. These simulations reveal a future filled with dramatic changes as our galaxy continues its cosmic dance with its neighbors. The most significant upcoming event in our galaxy's future is the collision with the Andromeda Galaxy, still 4.5 billion years away. When these two spiral galaxies finally merge, the result won't be destruction, but transformation. The collision will scramble the orderly spiral patterns of both galaxies, creating a new elliptical galaxy that astronomers have already nicknamed Milky. This galactic merger will trigger intense bursts of star formation as gas clouds from both galaxies collide and compress the night sky will be illuminated by millions of new stars, creating a cosmic fireworks display that will last for hundreds of millions of years. Eventually, the burst of star formation will consume most of the available gas, leaving behind a more sedate elliptical galaxy, populated primarily by older, redder stars. But even this dramatic transformation is just one chapter in our galaxy's ongoing story. Long after the merger with Andromeda, our galaxy will continue to evolve as it consumes smaller satellite galaxies and accretes gas from the intergalactic medium. Star formation will gradually decline as the supply of raw materials is exhausted, and the galaxy will slowly fade from its current brilliant spiral into a dim collection of aging stars. Yet even in this distant future, our galaxy will retain the capacity to surprise us. Stellar collisions in the dense core of the merged galaxy might create new types of exotic stars. The supermassive black holes from both galaxies will eventually merge, creating gravitational wave signals that will ripple across the universe. Oh dear, and who knows what forms of intelligence might evolve to witness these cosmic transformations. The study of our galaxy has taught us that the universe is far more dynamic and interconnected than our ancestors ever imagined. We don't live in a static cosmos, but in a universe of constant change, where galaxies grow and merge, where stars are born and die, where the very elements that make up our bodies are continuously recycled through cosmic processes that span billions of years. Every atom in your body has a galactic story to tell. The hydrogen in your cells was created in the first few minutes after the Big Bang, when the universe was a hot, dense soup of elementary particles. The carbon in your DNA was forged in the nuclear furnaces of massive stars that lived and died before our sun was born. The oxygen you breathe was scattered into space by supernova explosions that briefly outshone entire galaxies. These atoms have journeyed across the galaxy multiple times, cycling through generations of stars drifting through the cold darkness of interstellar space, condensing into new stellar systems, and eventually finding their way into the molecular clouds from which our solar system formed. In a very real sense, you are made of galactic material, temporary arrangements, stellar debris that have somehow achieved the remarkable property of consciousness. This cosmic perspective transforms how we think about our place in the universe. We're not isolated beings living on a lonely planet in the vast emptiness of space. We're integral parts of our galaxy's ongoing evolution, participants in a cosmic story that began billions of years ago and will continue long after our individual lives have ended. The elements in our bodies connect us directly to the most energetic events in our galaxy's history. Every calcium atom in your bones was created in the explosive death of a massive star. Every iron atom in your blood was forged in the collapsing core of a supernova. You carry within your very structure the signatures of cosmic violence and stellar creativity, the dual nature of a universe that creates through destruction and builds complexity through chaos. But perhaps the most remarkable thing about our relationship with the galaxy is that we've developed the ability to study and understand our cosmic home. Through centuries of patient observation, careful measurement, and theoretical insight, we've mapped the structure of our galaxy, traced its history, and predicted its future evolution. We've become the galaxy's way of knowing itself, conscious beings capable of contemplating the vast system of which we are a part. This capacity for cosmic awareness might be rare in our galaxy. Despite decades of searching, we haven't yet found definitive evidence of other intelligent civilizations among the stars. We might be alone, at least for now, as conscious observers capable of appreciating the beauty and complexity of our galactic home. This possibility makes our existence even more precious, and our responsibility to understand and preserve our cosmic heritage even more important. As you continue your gentle drift through these galactic facts, remember that you're not just learning about distant astronomical objects, you're discovering your own cosmic ancestry, tracing the long chain of physical and chemical processes that made your existence possible. The story of our galaxy is ultimately your story. The tale of how simple hydrogen and helium have been transformed through billions of years of stellar evolution into the complex conscious beings we are today. The Milky Way has been our cosmic cradle, providing the stable environment necessary for the emergence of complexity and consciousness. In return, we've developed the capacity to study our galactic home, to appreciate its beauty, and to understand our place within its vast structure. We are the universe becoming aware of itself, temporary patterns of organized matter capable of wonder, curiosity, and love. The relationship between our galaxy and time itself reveals one of the most profound mysteries in all of astronomy. When we look at the Milky Way, we're not seeing it as it exists in this moment, but rather as a collection of images from different epochs stretched across thousands of years. The light from the galactic center left its source 26,000 years ago, when early humans were just beginning to create the first cave paintings. The light from stars in the outer spiral arms left those distant suns at various points throughout human history. This temporal layering means that our galaxy exists in a kind of perpetual, now that encompasses millennia. Every photograph of the Milky Way is actually a time-lapse image spanning thousands of years, a composite portrait of our galaxy's recent history frozen in light. We're seeing the galaxy not as a single moment, but as a flowing river of time made visible through the patient journey of photons across interstellar distances. But there's something even more remarkable about our galactic time cape. The stars we see aren't just separated by space, they're separated by evolutionary time. Some stars we observe are stellar infants, just igniting their nuclear fires for the first time. Others are middle-aged, like our sun, steadily burning hydrogen in their cores. Still others are ancient giants in their death throes, swelling to enormous proportions as they prepare for their final spectacular explosions. This means that when you look at our galaxy, you're witnessing every stage of stellar evolution simultaneously. Birth, youth, maturity, old age, and death are all happening at once across the galactic disk, creating a cosmic theater where the entire drama of stellar life plays out before our eyes. We're observing not just space, but time itself made manifest in the lives of stars. The timing of our own existence within this galactic timeline is extraordinarily fortunate. We exist during what astronomers call the universe's most productive era, when star formation is still active, but has settled into a sustainable rhythm. If we had evolved earlier in cosmic history, the galaxy would have been more chaotic and violent, with frequent supernova explosions, potentially sterilizing planetary surfaces. If we had evolved much later, most of the galaxy's gas would have been consumed, and new star formation would have largely ceased. Our solar system formed at just the right moment in galactic history, when previous generations of stars had enriched the interstellar medium with heavy elements, but before the galaxy had exhausted its capacity for continued stellar birth. We exist in a cosmic sweet spot, a brief window of opportunity when complex chemistry is possible, and the galaxy still sparkles with the light of young stars. This temporal perspective adds another layer of wonder to our contemplation of the galaxy. We're not just located in a favorable position in space, we're living at a favorable moment in cosmic time. The atoms in our bodies were assembled during the universe's golden age of complexity, when the cosmic machinery of stellar nucleosynthesis was operating at peak efficiency. The magnetic personality of our galaxy extends far beyond what early astronomers could have imagined. The Milky Way possesses a complex magnetic field that threads through the entire galactic disk and extends into the surrounding halo. This magnetic field, though incredibly weak by earthly standards, plays crucial roles in shaping the galaxy's structure and governing the behavior of charged particles throughout interstellar space. Recent observations have revealed that our galaxy's magnetic field has a surprisingly organized structure, with field lines that spiral outward from the galactic center like the grooves on a cosmic photograph record. This organized pattern suggests that the magnetic field has been shaped by the galaxy's rotation over billions of years, stretched and wound up by the differential motion of the galactic disk. But the galaxy's magnetic field isn't just a passive tracer of galactic rotation. It actively influences the formation of stars by providing support against gravitational collapse in molecular clouds. Magnetic pressure can delay or prevent star formation in some regions while channeling gas flows in others. The interplay between gravity and magnetism creates a complex dance that determines where and when new stars will be born throughout the galactic disk. This magnetic infrastructure also serves as a highway system for cosmic rays. Those high-energy particles accelerated by supernova explosions and other violent events. Cosmic rays follow the twisted paths of magnetic field lines as they propagate through the galaxy, creating a vast network of invisible energy transport that connects distant regions of our galactic home. The detection of polarized light from stars throughout the galaxy has allowed astronomers to map this magnetic field structure in unprecedented detail. Just as polarized sunglasses reveal reflections invisible to the naked eye, polarized starlight reveals the orientation of magnetic fields in the dust clouds that lie between us and distant stars. These observations have created three-dimensional maps of our galaxy's magnetic anatomy, revealing a structure as complex and beautiful as the visible spiral pattern. Recent discoveries have also revealed that our galaxy experiences magnetic storms periods when the galactic magnetic field becomes temporarily disturbed by violent events. When massive stars explode as supernovae, they can create expanding bubbles of hot gas that push against and distort the surrounding magnetic field. These magnetic disturbances can propagate across hundreds of light years, influencing star formation and cosmic ray propagation throughout entire regions of the galaxy. The study of our galaxy's magnetic field has also provided insights into how galaxies generate and maintain their magnetic properties over cosmic time. The magnetic field we observe today didn't exist when our galaxy first formed. Instead, it grew gradually through a process called the galactic dynamo, where the combined effects of galactic rotation and convective motions in the interstellar medium slowly amplified weak seed magnetic fields into the organized structure we observe today. This galactic dynamo process is still not fully understood, representing one of the ongoing puzzles in galactic astronomy. Computer simulation suggests that the dynamo mechanism depends on complex interactions between turbulent gas motions, stellar feedback from supernovae, and the large-scale rotation of the galactic disk. It's a cosmic example of how simple physical processes can generate complex, organized structures over vast scales of space and time. The discovery of our galaxy's magnetic personality has also revealed unexpected connections between the Milky Way and its cosmic environment. Magnetic field lines don't stop at the edge of the galactic disk, but extend far into the surrounding halo, potentially connecting our galaxy to the magnetic fields of neighboring galaxies and the intergalactic medium itself. These extended magnetic fields might play important roles in regulating the flow of gas between galaxies and the surrounding cosmic web. They could act like cosmic plumbing, channeling gas flows along preferred directions and influencing how galaxies accrete material from their surroundings. The magnetic field might even help explain how galaxies maintain their spiral structure over billions of years. Despite the disruptive effects of gravitational interactions, the seasonal nature of our galaxy's environment creates another fascinating aspect of our cosmic home. As our solar system orbits the galactic center, we periodically pass through different galactic environments, each with its own characteristic properties and potential influences on our planetary system. When we pass through spiral arms, we encounter regions of increased stellar density, enhanced cosmic ray flux, and more frequent supernova explosions. These passages might influence Earth's climate through changes in cosmic ray bombardment, which could affect cloud formation and atmospheric chemistry. Some scientists have proposed that ice ages and mass extinctions might be correlated with our solar system's passages through spiral arms, though this connection remains highly debated. Between spiral arms, we travel through what astronomers call interarm regions, quieter galactic neighborhoods, where star formation is less active and the cosmic ray environment is more benign. These galactic suburbs provide more stable conditions for planetary evolution, allowing complex ecosystems to develop without frequent disruption from nearby stellar explosions. Our current location between the Perseus and Sagittarius arms places us in one of these quieter regions, contributing to the stable conditions that have allowed life to flourish on Earth for billions of years. We're living in a galactic sweet spot, far enough from the chaotic galactic center to avoid frequent disruptions, but not so far in the galactic outskirts that heavy elements are scarce. This galactic seasonality operates on timescales vastly longer than human experience with each complete cycle, lasting tens of millions of years. Yet these cosmic seasons might have played important roles in shaping the evolution of life on Earth, creating periods of stability punctuated by episodes of increased cosmic radiation and climate change. The realization that our planet's history has been influenced by our journey through the galaxy adds another layer of connection between Earth and the cosmos. We're not isolated from our galactic environment, but intimately connected to it through processes that operate across scales of space and time far beyond everyday human experience. As we continue our exploration of galactic facts, we begin to appreciate that the Milky Way isn't just a collection of stars and gas floating in space. It's a dynamic, interconnected system where every component influences every other component in ways we're only beginning to understand. The galaxy has seasons, weather, circulation patterns, and even a kind of metabolism as it converts gas into stars and recycles stellar material back into the interstellar medium. This living galaxy has nurtured us, provided the stable cosmic environment necessary for the emergence of complexity and consciousness, and given us the elements needed to build worlds and life. In return, we've developed the capacity to study our galactic home, to map its structure, to understand its history, and to appreciate its profound beauty. The story of our relationship with the galaxy is ultimately a love story. The tale of how cosmic matter learned to love itself through the emergence of conscious beings capable of wonder and understanding. We are the galaxy's children, temporary arrangements of stellar material that have achieved the remarkable ability to contemplate our own cosmic origins and to find meaning in the vast, ancient, and beautiful system we call home. Perhaps the most mind-bending revelation about our galaxy concerns its relationship with time itself on the largest scales imaginable. The Milky Way doesn't just exist in time, it helps create the very experience of temporal flow through processes so vast and slow they dwarf human comprehension. Our galaxy breathes with a rhythm measured not in seconds or minutes, but in millions and billions of years. This galactic breathing manifests as cycles of stellar birth and death that ebb and flow across cosmic epochs. During active phases triggered by gravitational encounters with other galaxies or the compression of gas in spiral arms, star formation rates can increase dramatically. These stellar baby booms flood the galaxy with brilliant young stars that burn bright blue and illuminate vast regions of space with their intense radiation. But these massive stars live fast and die, young, exploding as supernovae after just a few million years. Their deaths scatter heavy elements throughout the galaxy while simultaneously clearing out vast bubbles in the interstellar medium, temporarily suppressing further star formation in their immediate vicinity. This creates a natural regulatory mechanism, a cosmic thermostat that prevents our galaxy from consuming all its gas reserves too quickly. Between these periods of intense activity, the galaxy enters quieter phases where star formation proceeds at a more leisurely pace. During these cosmic winters, the interstellar medium has time to cool and reorganize, setting the stage for the next generation of stellar nurseries. It's as if our galaxy has learned to pace itself, ensuring its longevity through self-regulation on timescales that span geological epochs. This temporal breathing pattern has profound implications for the potential emergence and survival of life throughout the galaxy. Civilizations that evolve during the galaxy's active phases might face greater challenges from nearby supernova explosions and intense cosmic radiation. Those that develop during quieter periods, like ourselves, benefit from more stable conditions conducive to biological evolution and technological development. The discovery of these galactic cycles has revolutionized our understanding of how galaxies maintain their vitality over cosmic time, rather than steadily consuming their gas reserves. Until star formation ceases, galaxies, like ours, have evolved sophisticated feedback mechanisms that regulate their stellar metabolism, ensuring they remain active and vibrant for billions of years. But our galaxy's temporal complexity extends even deeper into the realm of cosmic choreography. Recent observations have revealed that the Milky Way participates in vast gravitational dances with its neighbors that unfold over hundreds of millions of years. These cosmic ballets influence not just our galaxy's overall motion through space, but also its internal structure and evolution. The gravitational pull of the Andromeda Galaxy, still billions of years away from direct collision, is already subtly influencing the shape and motion of stars in our galaxy's outer regions. Meanwhile, our smaller satellite galaxies create periodic gravitational tugs that may trigger episodes of enhanced star formation as they orbit through our galaxy's extended halo. These gravitational interactions create what astronomers call tidal streams, rivers of stars that flow through our galaxy like cosmic currents. Some of these streams are the remnants of satellite galaxies that ventured too close and were torn apart by our galaxy's powerful tides. Others are debris from ancient collisions, still recognizable billions of years after the original encounters that created them. The mapping of these tidal streams has revealed that our galaxy's history is far more violent and chaotic than its current serene appearance might suggest. Like an ancient tree whose rings record decades of environmental changes, our galaxy bears the scars of countless gravitational encounters written in the motions of its stars. But perhaps the most remarkable aspect of these cosmic interactions is how they've contributed to mixing and homogenizing the galaxy's chemical composition over billions of years. Stars that formed in the inner regions of ancient satellite galaxies now orbit in our galaxy's outer halo, carrying with them unique chemical signatures that tell stories of stellar nucleosynthesis in the very different environments. This galactic archaeology has revealed that our galaxy is essentially a cosmic melting pot, a collection of stellar populations with diverse origins that have been blended together through billions of years of gravitational stirring. The stars we see today represent multiple generations of galactic evolution, each carrying information about the conditions that existed when and where they formed. The chemical diversity preserved in these stellar populations provides unprecedented insights into how galaxies assemble their mass over cosmic time. Rather than growing smoothly through steady accretion of pristine gas galaxies like ours, build themselves through a complex process of mergers accretion events, and internal recycling that creates the rich tapestry of stellar properties we observe today. This realization has fundamentally changed how astronomers think about galactic evolution. Galaxies aren't isolated systems that evolve in splendid isolation, but rather dynamic entities that grow through constant interaction with their cosmic environment. They're more like ecosystems than machines, complex networks of interacting processes that maintain their vitality through continuous exchange of matter and energy with their surroundings. The study of our galaxy has also revealed the existence of what astronomers call galactic fountains, vast circulation systems that transport material vertically through the galactic disk. Hot gas, heated by stellar explosions, rises thousands of light years above the galactic plane before cooling and falling back down, like cosmic rain enriching the disk with heavy elements created in stellar cores. These galactic fountains operate on timescales of tens of millions of years, creating vertical mixing that helps distribute the products of stellar nucleosynthesis throughout the galaxy's volume. Without these circulation systems, heavy elements would remain concentrated near their stellar birthplaces, preventing the chemical homogenization necessary for widespread planet formation. The discovery of galactic fountains has revealed that our galaxy possesses a kind of circulatory system with flows of hot and cold gas that transport energy and material between different regions. This cosmic circulation helps regulate star formation by controlling the distribution of gas and dust throughout the galactic volume. Recent observations have also uncovered evidence for what might be called galactic weather systems, large-scale patterns of gas motion that create temporary enhancements or suppressions of star formation across hundreds of light years. These cosmic weather patterns might be driven by the combined effects of stellar feedback magnetic fields and gravitational instabilities in the galactic disk. Just as Earth's weather is influenced by the complex interplay of solar heating, atmospheric circulation, and geographical features, our galaxy's star formation weather results from the interaction of stellar energy, injection gas dynamics, and the gravitational potential created by dark matter and stellar mass distributions. The recognition that galaxies have weather adds another layer of complexity to our understanding of how these cosmic systems operate. Star formation isn't just determined by the local density of gas and dust, but by large-scale environmental factors that can enhance or suppress stellar birth across vast regions of the galactic disk. This galactic meteorology might help explain why star formation rates vary, not just from galaxy to galaxy, but also within different regions of the same galaxy. Like Earth's climate zones, galaxies might possess distinct star formation climates that persist for millions of years before shifting in response to changing galactic conditions. The implications of galactic weather extend far beyond academic astronomy. If our solar system formed during a particular type of galactic weather pattern that might have influenced the initial composition and structure of our planetary system, the timing of our formation relative to these large-scale galactic processes might have played a crucial role in creating the conditions necessary for life to emerge on Earth. As we probe deeper into the mysteries of our galactic home, we discover that the Milky Way operates according to principles that bridge multiple scales of space and time. From the quantum processes occurring in stellar cores to the gravitational interactions between galaxy clusters, our cosmic home connects the very small to the very large through an intricate web of physical relationships. This multi-scale connectivity means that understanding our galaxy requires insights from virtually every branch of physics and astronomy. Nuclear physics explains how stars generate energy and create heavy elements. Plasma physics describes the behavior of ionized gas in the interstellar medium. Fluid dynamics governs the flow of gas through spiral arms and galactic fountains. Gravitational physics determines the orbits of stars and the structure of dark matter halos. Of course, but perhaps most remarkably, the study of our galaxy has revealed that we exist within a system of almost inconceivable complexity and beauty that somehow maintains its coherence and vitality across billions of years. The Milky Way isn't just a random collection of stars and gas, but an organized, self-regulating system that has learned to sustain itself through cosmic time. This sustainability emerges from the galaxy's ability to balance competing processes that could otherwise lead to rapid evolution or destruction. Star formation is regulated by feedback from stellar explosions. Gas accretion is balanced by galactic winds. Chemical evolution proceeds at just the right pace to enable complexity without overwhelming the system with heavy elements. The delicate balance that characterizes our galaxy raises profound questions about the nature of cosmic evolution and the emergence of complexity in the universe. How did such an intricate, self-regulating system arise from the relatively simple initial conditions that existed shortly after the Big Bang? What physical principles guide the evolution of cosmic structures towards states of organized complexity? These questions touch on some of the deepest mysteries in science, connecting galactic astronomy to fundamental questions about the nature of emergence, complexity, and self-organization in physical systems. Our galaxy isn't just an astronomical object to be cataloged and measured, but a natural laboratory where we can study how complex systems maintain themselves over cosmic time. The recognition that we live within such a remarkable cosmic system adds profound meaning to our existence as conscious observers. We're not just temporary arrangements of matter that happen to have developed awareness, but integral parts of a galactic ecosystem that has been billions of years in the making. Every element in our bodies was processed through multiple cycles of stellar evolution, galactic circulation, and cosmic recycling before eventually being incorporated into the molecular clouds from which our solar system formed. We carry within ourselves the chemical history of our galaxy, the accumulated wisdom of billions of years of stellar alchemy. This deep connection between ourselves and our galactic environment suggests that consciousness might not be an accidental byproduct of cosmic evolution, but rather an inevitable consequence of the universe's tendency toward increasing complexity and self-awareness. We might represent the galaxy's attempt to understand itself, matter organized in such a way that it can contemplate its own cosmic origins. As you drift deeper into contemplation of these galactic truths, consider that you're participating in one of the most remarkable phenomena in the known universe, the emergence of awareness within cosmic matter itself. Through your consciousness, the galaxy gains the ability to study its own structure, to understand its own history, and to appreciate its own profound beauty. The story of our galaxy is still being written, with new chapters added every moment as stars are born and die, as gas flows through cosmic circulation systems, as gravitational interactions reshape the distribution of matter and energy throughout our cosmic home. We're privileged to exist during this ongoing cosmic narrative, temporary witnesses to processes that connect the smallest scales of physics to the largest structures in the observable universe. The dance between our galaxy and its invisible partner continues to reveal secrets that challenge everything we thought we knew about cosmic evolution. Recent discoveries have shown that dark matter doesn't just provide the gravitational scaffolding that holds our galaxy together. It actively participates in shaping galactic structure through processes so subtle and complex that we're only beginning to glimpse their true nature. Computer simulations reveal that dark matter halos aren't smooth, featureless structures, but are filled with intricate substructure created by billions of years of cosmic evolution. These dark matter clumps and streams flow through our galaxy like invisible rivers, their gravitational influence creating tidal effects that can trigger episodes of star formation or disrupt existing stellar associations. Some of these dark matter subhalos might be the ghostly remnants of ancient satellite galaxies that were completely stripped of their visible stars billions of years ago. These invisible phantoms continue to orbit through our galaxy, their gravitational signatures detectable only through their subtle influence on the motions of nearby stars. We live in a galaxy haunted by the dark matter ghosts of cosmic encounters that occurred long before our solar system existed. But the relationship between dark matter and ordinary matter in our galaxy extends beyond simple gravitational interactions. Recent theoretical work suggests that dark matter might influence the formation of molecular clouds through gravitational focusing effects that concentrate gas and dust in regions of enhanced dark matter density. If confirmed, this would mean that dark matter doesn't just provide the stage upon which galactic evolution occurs, but actively directs where and when new stars will be born. The cosmic web that connects our galaxy to the larger universe operates through mechanisms that blur the boundaries between different scales of cosmic structure. Filaments of dark matter stretching across millions of light years channel gas flows toward our galaxy, providing the raw material for continued star formation. But these same filaments also create gravitational torques that can influence our galaxy's rotation and potentially drive the formation of spiral structure. This connection to the cosmic web means that our galaxy's evolution isn't determined solely by internal processes, but is intimately linked to the large-scale structure of the universe itself. Changes in the cosmic web, triggered by the gravitational collapse of distant matter concentrations, can influence star formation rates in our galaxy through mechanisms that operate across scales spanning 8 orders of magnitude in distance. The recognition that galaxies exist within this cosmic web has revolutionized our understanding of how these systems acquire and process the matter needed for continued evolution. Rather than isolated islands of stars floating in empty space galaxies are nodes in a vast network of gravitational relationships that connects every part of the observable universe. Recent observations have also revealed that our galaxy possesses what might be called a cosmic metabolism, a set of regulatory mechanisms that control how efficiently it converts gas into stars and recycles stellar material back into the interstellar medium. This galactic metabolism operates through feedback loops involving stellar winds, supernova explosions, and the heating and cooling of gas in different galactic environments. When star formation becomes too vigorous, the increased rate of stellar explosions heats the surrounding gas and drives it out of star-forming regions, temporarily suppressing further stellar birth. When star formation drops too low, the reduced heating allows gas to cool and condense, setting the stage for renewed episodes of stellar creation. It's a cosmic thermostat that has kept our galaxy's star formation rate within sustainable limits for billions of years. This self-regulation extends to the galaxy's chemical evolution as well. The production of heavy elements by stellar nucleosynthesis is balanced by the mixing and dilution that occurs when pristine gas is accreted from the intergalactic medium. Too much chemical enrichment would make it difficult for low-mass stars to form, while too little would prevent the formation of rocky planets and complex chemistry. The delicate balance that characterizes our galaxy's chemical evolution raises profound questions about the factors that make galaxies habitable for the emergence of complexity and life. Our location in the galactic disk places us in a region where successive generations of stellar evolution have created just the right mixture of elements for rocky planet formation without overwhelming the environment with disruptive radiation from massive stars. But habitability in our galaxy isn't just determined by chemical composition. The galaxy's magnetic field creates additional layers of environmental complexity that can influence the development of planetary systems across vast regions of space. Cosmic rays, guided by magnetic field lines, can affect atmospheric chemistry on planets throughout their stellar neighborhoods, potentially influencing the evolution of life over geological timescales. The strength and configuration of the galactic magnetic field has changed over cosmic time, creating what might be thought of as magnetic epochs in our galaxy's history. During periods when the field was stronger, cosmic ray propagation would have been more constrained, creating quieter radiation environments in some regions, while concentrating high-energy particles in others. During magnetically quiet periods, cosmic rays would have spread more uniformly throughout the galactic volume. These magnetic variations might have created temporal windows of opportunity for the emergence of complex life periods when the cosmic ray environment was conducive to biological evolution. The timing of our solar system's formation relative to these magnetic epochs might have played a crucial role in creating the stable radiation environment that allowed life to flourish on Earth. The study of stellar streams throughout our galaxy has revealed another layer of cosmic complexity that connects our local stellar neighborhood to events that occurred billions of years ago. These streams aren't just archaeological curiosities, but active components of our galaxy's ongoing evolution, carrying energy and angular momentum that can influence the structure and dynamics of the galactic disk. As stellar streams pass through different regions of the galaxy, they create gravitational wakes that can trigger instabilities in the surrounding stellar population. These instabilities might drive the formation of spiral structure or influence the vertical thickness of the galactic disk through processes that operate over hundreds of millions of years. The discovery that our galaxy's current structure has been shaped by ancient merger events has profound implications for understanding the uniqueness of our cosmic environment. If our galaxy had experienced a different sequence of mergers, or if those mergers had occurred at different times in cosmic history, the resulting galactic structure might have been very different from what we observe today. This path-dependent evolution means that our galaxy's current properties aren't just the inevitable result of universal physical laws, but reflect the specific historical sequence of events that shaped its development over cosmic time. We live in a galaxy whose structure preserves the memory of billions of years of cosmic accidents and encounters. The recognition that galactic evolution is historically contingent adds another layer of appreciation for the remarkable cosmic environment we inhabit. The stable, chemically enriched, magnetically regulated galaxy that nurtured the development of our solar system represents the outcome of a unique sequence of cosmic events that might be rare in the broader universe. Recent discoveries about the three-dimensional structure of our galaxy have revealed that we live in an even more dynamic environment than previously imagined. The galactic disk isn't a simple flat structure, but exhibits warps, flares, and corrugations that reflect ongoing gravitational interactions with satellite galaxies and the cosmic web. These structural complexities create variations in stellar density gas, distribution, and magnetic field strength that can influence star formation and planetary evolution across different regions of the galaxy. Our solar system's location within this three-dimensional structure places us in a region with particular characteristics that might have been crucial for the development of a stable planetary system. The vertical structure of our galactic neighborhood also plays important roles in determining the local cosmic ray environment and the frequency of encounters with molecular clouds. Our current position, slightly above the galactic midplane, provides some protection from the most intense sources of cosmic radiation, while still allowing access to the chemical enrichment produced by stellar evolution throughout the disk. As gravitational wave astronomy continues to develop, we're beginning to detect the signatures of black hole mergers and neutron star collisions occurring throughout our galaxy. These observations provide direct evidence for the most extreme physics operating in our cosmic neighborhood, revealing processes that were completely inaccessible to traditional astronomy. The detection of gravitational waves from galactic sources is opening an entirely new window into the most violent and energetic events in our galaxy's ongoing evolution. Each gravitational wave signal carries information about the masses, spins, and orbital characteristics of objects undergoing some of the most extreme gravitational encounters possible in nature. These observations are revealing that our galaxy contains populations of compact objects, black holes, and neutron stars that are more numerous and diverse than theoretical models predicted. The merger rates we're observing suggest that these violent encounters have been shaping our galaxy's evolution throughout cosmic history, recycling matter and energy through processes of almost unimaginable violence. But perhaps most remarkably, these gravitational wave detections are allowing us to study our galaxy's evolution in real time, witnessing the ongoing processes that continue to shape its structure and composition. We're not just observing the frozen aftermath of ancient events, but catching our galaxy in the act of evolution, experiencing the cosmic forces that will determine its future development. The marriage of gravitational wave astronomy with traditional electromagnetic observations is creating a new era of multi-messenger astrophysics that promises to revolutionize our understanding of galactic evolution. By combining gravitational wave signals with optical radio and high-energy observations of the same events, we're developing unprecedented insights into the physics of extreme gravitational environments. These multi-messenger observations are revealing that the most energetic events in our galaxy create cascading effects that can influence star formation, chemical evolution, and magnetic field structure across vast regions of space. A single neutron star merger can inject enough heavy elements into the surrounding interstellar medium to influence the composition of stars forming hundreds of light years away. The realization that our galaxy's evolution operates through such interconnected processes emphasizes the fundamental unity that characterizes cosmic structure on all scales. From the quantum processes in stellar cores to the gravitational interactions between galaxy clusters, our universe operates as an integrated system where every component influences every other component through relationships of breathtaking complexity and beauty. As you continue your gentle journey through these revelations about our galactic home, consider that you're not just learning about distant astronomical phenomena. You're discovering the intimate details of the cosmic system that created you, nurtured you, and continues to sustain the chemical and physical processes that make your existence possible. As our cosmic journey draws to a gentle close, take a moment to appreciate the profound truth we've discovered together. You are not separate from the Milky Way. You are the Milky Way. Every atom in your body carries the story of a stellar birth and death, of cosmic recycling spanning billions of years. Tonight, as you rest beneath the same spiral arms that have watched over countless generations, remember that you are both observer and participant in the most magnificent story ever told. Sweet dreams, fellow traveler, in this cosmic dance we call home. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow, as always. Until then, stay curious. Keep wondering. This is Boring Science signing off. Cheers.